Hi, everyone. Thank you for having me today. I'm really excited to share with you our research on visualization for deep learning. And I call it an Odyssey because it's been a few years since we started working on it. And my name is Polo. I'm Associate Professor at Georgia Tech, and I'm also Associate Director of our Analytics Master's program there. I would like to start the talk by giving you an overview of the research that we do at Georgia Tech. My group is called the Polo Club of Data Science, and we work at the intersection of artificial intelligence and human intelligence. The main idea is to how to combine the best of both worlds so that we can develop scalable, interpretable, and trustworthy tools that help people make sense of complex large-scale data set and models. And I always like to thank my students, my PhD student at the top left, and then my master's student and undergraduate student in the middle and on the right-hand side, and also our recent alum at the bottom. And because a lot of the work that you see today is work that is done by them. And these days we are working on two major research threads, safe AI and interpretable AI. Safe AI means how do we protect the AI models from harm, and also how do we identify vulnerabilities. And interpretable AI means how do we help people understand what these models are doing. And today's focus is on the second one, particularly on how to use visualization to help with interpretation. And you will see that a lot of examples that we provide are actually motivated by safe AI. So that means how do we help people understand what these AIs are doing when they're doing well, and also when they're not doing well, why is that? I'll give you an example of what I mean by that. So you probably know that AI these days are often used in safety critical application, for example, in self-driving cars. So unfortunate example that you may have seen in news that this Uber accident where a pedestrian was killed in Arizona when the pedestrian was crossing the road and the car was not able to recognize that person in time. So for that reason, safe AI probably quite easy for people to understand. Okay, so since AI is now using these applications, then we really need to protect them and also to identify their vulnerabilities. I have another more interesting example. So our group has been working on attack and defenses, and as part of the DARPA GARD program. GARD stands for Guaranteeing AI Robustness Against Deception. And we developed a technique called shapeshifter, which you can craft these we call adversarial patterns that can fool even state-of-the-art object detectors. So what I'm going to show you here is a very brief video to make the case of how real these threats can be. So on the left-hand side on the screen, you'll see that real stop sign. And on the right-hand side is a adversarial stop sign that the shapeshifter technique will be able to generate. So I'm going to play the video. So the actual video taken by a former graduate student, Zhangji Chen, who's now assistant professor at National Taiwan University. So if we drive the car closer and closer to the two stop sign, you will see that the real stop sign is correctly detected. While on the fake stop sign, we actually don't get detected as the car drives closer. And it's only getting detected as a lot of people, and when they're really, really close. So in fact, you can actually craft these adversarial patterns to be anything that you want. So this is pretty scary, actually. So that means you can now have these physically realizable attack pattern that can fool even state-of-the-art object detector. So of course, when we study these attack and defenses, our ultimate goal is to develop defenses for AI so they can protect them from harm, whether intentional harm or unintentional harm. But one thing that people often don't talk about is that we don't really know how these defenses work. Even if you have a defense, you just say, oh, the accuracy looks good, so now it's more accurate, so probably your AI is protected. We think that we can do better. We don't think that we should treat these models as black boxes. Rather, what we may want to do is to make that a little bit more translucent. We call it interpretable AI. So our main ideas is to develop scalable interactive visual tools to help people understand these complex large-scale machine learning systems. And that brings us to our today's topic, which is visualization for deep learning, which is all about what we do about interpretable AI. And I call it an Odyssey, and because it actually started way back in 2016 summer. And of course, it extended all the way to today. And everything that got started was actually due to a summer internship, which led to the Activis system, which is a way to scalably interpret an industry scale model at Facebook or now Meta. And that led to a whole line of research on scalable interpretation tools. And then from there, then we use a lot of that to help us understand vulnerabilities and biases. That's another line of research And then when we are developing these techniques, then that actually got us thinking, oh, actually, you know what? Sometimes we may not even know how these models work. So that means there's a need for learning, whether for experts or even for students, and that led us to develop the line of research on interactive education, where we build tools to help people learn how these models work. So for today, I'm going to give you a few examples in all these three categories. And I'm going to start with the very first one, the Activis tool under scalable interpretation, which started everything that we do over these past 6-7 years. So Activis started as an internship project by Dr. Min-Seok Khan. So he's actually now an assistant professor at Oregon State University. And back then, during that summer, he was working at Facebook, and now it's called Meta. And the main goal there is to how to help the data scientists at Meta to understand what the models are doing, what they're learning. And they really need these tools to interpret complex models because they're actually dealing with a lot of models. So in other words, they have a lot of practical challenges they need to handle. For example, a lot of the models that deal with are very deep or very wide. So they could have tens of thousands of operations or layers. And their data set often are also very large. There could be billions of instances. And also they're dealing with different kinds of data, like text data, numerical data, categorical data, and so on. So to help develop this visualization tool, then that very naturally, the first step was to understand the user needs at Meta. So through a participatory design session with 15 researchers and engineers and data science over 11 months, what Min-Seok developed was the Activis system that can scalably visualize the industry scale model at Meta. And it was deployed by Meta and used by a lot of engineers at Meta. So what are the particular challenges that are used, that we deal with by Activis? So there are three primary challenges. So I'll go through each of them and also present the solution that Activis came up with. So challenge number one was that the models often have a lot of parameters. So that means that visualizing every single one of them, then probably not ideal. So our main observation is that even though there may be a lot of layers in a deep learning model, for example, not everything is equally important. So we can show the ones that are particularly useful, for example, a particular layer that's more important, then we focus on that. So to help using that observation, then in the Activis tool, then we provide what we call the model architecture overview, where we show the whole architecture, and we allow the user to zoom and pan to explore the computation graph. So, and they can look at the component that they're interested in, and if they're interested in it, they can click on it. And then at the bottom, then they can see in more detail. We call it neuron activation view. So that means in that component, how are neurons activated strongly or in other ways. The second challenge that Activis handles was to deal with the many data instances that Meta has. And we observed two primary analytics patterns. One is what we call instance level analysis, and then the other is subset level analysis, and both of them are equally important. So instance level here means that particular data examples that the user may be interested in looking at. And this is often really helpful for debugging. It's kind of like when we're doing programming, we may have specific test cases. So that is what we mean by instance level. And of course, at Meta, a lot of data sets are really big. So that means you cannot really look at every single instances by yourself. So that means some aggregation or summarization is important. And so this is what we call subset level. And note that subset here could mean a class, or it could be a user-defined subset of the data set. So the key question here is that how do we unify? How do we provide a way for the user to do both instance level and subset level analysis? So that gave us the idea of what we call a unified analysis design for both instances and subset. Concretely, that means in our neuron activation view, here we provide the neuron matrix view, where each row here could be an instance, or it could be an instance subset. And then the columns here are the neuron. So that means we put all the instances, classes, user-defined subsets, all of them in a single view. So here we are showing an example of text data, and then they are of one of the 6 classes, where a piece of text could be about description, about entity, about abbreviation, and so on. So those are shown at the top. And then in the middle, these are what we call user-defined subset. So that means the user could say, I only want text that contains like the word how many, how, and so on. And then on the right-hand side of Activis, this is where the user can select particular instances, and when you click on them, they get added to the matrix view. So each row here would be an instance. And again, because all the columns are the same, so that means here we can use the activation strength to be encoded as the darkness of the neuron. So that means we have a combination of subsets and also instances, and all of them in a single view. And as I mentioned, instance analysis is really helpful for debugging. So here, what we just saw was that we can actually order the neurons based on the activation strength. So by doing so, then we can see that, so for the instances that correctly classified, they're actually quite correlated with the correct class. And then for the misclassified instances, they are less correlated. So we can do all these in a single view. The third challenge that activists deal with is how to handle the scale of data that Meta is handling. And we accomplish that by three main ideas. One is what we call user-guided instance sampling. So that means a user can provide preference for what kind of instances they may want to look at, so that we can do the pre-computation there. And second idea is the pre-computation of layers. So as we mentioned before, not all layers are equally important. So the user can select what they want to pre-compute, and then we can do that beforehand. And thirdly, we also do the matrix computation, a lot of these, through the Meta's platform, so that we can handle these billion scales instances. And Activis have been deployed on the FBLearner platform, Meta's machine learning platform that's used by over 25% of engineering team. So what that means is that once a user has a model trained, then they can just do one click, and then they can launch Activis. So when you're looking at Activis, one thing you might have noticed is that it mainly focuses on inspecting neurons, individual neurons. So what it has not do is to look at the interaction of the relationships between neurons. So that means, like, how do we know if two neurons are related, and in what way? So that prompted us to develop a system called Summit, which particularly aimed to address that problem. So here I'm showing you an example of what we mean by looking at the relationship among neurons. So let's say you are dealing with the ImageNet dataset that has like 1,000 classes, and one of the classes is called a white wolf class, so a lot of wolf images. And you probably have heard a lot about what people say, so they have, like, if you have a deep neural network doing classification, and if it's very good at classifying white wolf images, then probably has learned features like white fur, you might have learned like pointy ear, licks, and so on. And then the networks that connect all of these together and then make the final prediction of white wolf. Right, so this is what a lot of people have been talking about. But the question is that really happening inside the model? So that's what Summit is trying to do. So it tries to identify these fur, ear, licks feature, and also the connection among them, and then show them as a graph. So that means, in a nutshell, Summit is trying to scalably summarize and interactively visualize these feature representations and their relations for millions of images. So I'm going to show you quickly a demo of Summit. Here I'm using the Tench class. So Tench is yellowfish, is one of the 1,000 classes in ImageNet. And on the right-hand side of the Summit tool here, you will see this is the graph summary that we just described. So that means each neuron here is a node, and then edges are the connection among the neurons. So further to the top, that means closer to the prediction, and then further to the bottom, that means that there's a more lower level features. So I'm mousing over some of the neurons, and here when I mouse over one neuron, I will see some what we call a dataset example. So that means some image patches from the real dataset that strongly activate this particular neurons. So perhaps to your surprise, that you may find that even though this class is Tench, which is fish class, you don't really see fish features. Rather, what you see is human features like faces and hands, and only when you're getting to the higher layer that you start to see some fish. But you still see quite a bit of people still, right? So now it's a little bit more fish. And you can actually try it live. Like, go to fredholman.com and Summit. This is a live tool, exactly the one that I just showed, and try it yourself. So the question here for you is then, why are we seeing all these human feature, even though our classification task is about Tench fish? Right? So usually I would do it as a quiz interactively, but here I'm just going to show you the answer. It turned out that Tench is the kind of fish that is very big, so people like to catch them and then take picture of. So that means in the whole ImageNet data set, even though the 10 class prediction is really accurate, it's actually using people feature to do the classification. So that really back to the question, like, would you feel comfortable in using the model now that you know what it's really using to do the prediction? Maybe yes, maybe no. Yes, as in if there's a kind of images that you are classifying, or maybe no, if you're only dealing with images with fish, but not people. So something I gloss over a little bit is about the graph. So particularly how we generate the graph. We call this an attribution graph because the graph, we can attribute the particular prediction, or through the graph, we can attribute a particular prediction to individual neurons and their relationships. And something you notice that the attribution graph is actually a very small subset or subgraph of the whole network, which has a lot of neurons and a lot of edges. So the question is, how do we do such a summarization? So the main idea is through ranking. So particularly for the neurons or the nodes in the graph, we identify the activation string by passing through all the images of a class through those neurons, and then we take the maximum value of the neuron. And we take the top ranked ones, and then we throw away the ones that are much less strongly activated. And we do this for all the neurons in one layer and also for all the other layers. And we scale the neurons, the node size based on the neuron's activation strength. And we do the similar procedure for the edges. So suppose we have a neuron already filtered and to be included in one layer. Now we go back to the layer before that. And then we look at how, which of the neurons are most strongly influencing the particular neuron. So again, we take the max of the activation or the influences, and then we do the ranking, and then we throw away the ones that are not as strong and only keep the ones that are the strongest. So that means now we can do the filtering of edges. Right? And we apply the same idea to all the edges in the whole graph, and we end up getting the attribution graph. So something you may have noticed is that in Summit, or actually any deep neural network, there's quite a bit of redundancy. So that means that we have multiple neurons or multiple nodes that are actually detecting the same thing. For example, here I'm going to show you an example where we have some dot images, which are the rows. And as we pass these dot images to the neurons, here we're showing you only two, but there are actually a lot more neurons, neuron 460 and 483. These two neurons actually get activated in very similar way, not identical, but very, very similar. So the question then now is that, well, can we actually identify or group all these similar neurons so that we can reduce the redundancy, and more importantly, to help with interpretation, because then people can look at only groups of neurons rather than individual neurons. So that's exactly what we did. So we group these neurons through a technique called locative sensitive hashing that allow us to group these neurons by only doing a linear pass through all the neurons instead of doing like n-square comparison where n is the number of neurons across all the possible pairs. And that's a NeuroCartography approach which was published in VIS 2021. So the main idea is very similar to Summit in terms of the graph summarization. The main difference here is actually part D in the screenshot shown here, where we can group all the neurons automatically and very scalably. So each row in part D is one neuron. So that means we are showing here at least 4. Actually, they have even more. Like I said, a scroll bar, we're not showing all of them. So all these 4 neurons are about dog faces. So something you may ask is that, well, so it's scalable, but how good is it? And really finding or grouping these neurons. So we did a user study through Mechanical Turk. We asked 244 workers to rate the neurons or the grouping that was found by NeuroCartography. So on the right-hand side, I show an example task that a worker would complete. So we will show the worker 5 neurons, each one represented by the 9 image patches. And then also we inject what we call intruder neuron. So that means it's a random neuron that's very unlikely to be related to the other 5 neurons. So here, 5 out of 5 neurons, you can see this is actually the Dalmatian spot of dot. So through this setup, then we ask the Mechanical Turk workers to identify which ones out of all the 6 belong to the same group and which one does not. So through this kind of rating, then we can get both the true positive and the true negative, and also the false negative and true positive as well, all this rating, and then we can plot this in the ROC curve. So you see that for NeuroCartography, we achieve an AUC score of 0.91, where for handpick, so that means this is manual, the highest quality kind of grouping is AUC of 0.97. So it's pretty close, not perfect, but it's pretty close, and definitely much, much better than random choices, which is AUC score of 0.5. So far what you've seen is the Summit and NeuroCartography system, and the main idea is to do scalable graph-based visual summarization of what the neural network has learned. So a question that you may ask is, well, so it's helpful for understanding when a model is working well. So what about when a model is not working well? So can Summit or NeuroCartography be helpful? Short answer is yes. So that is exactly the motivation for why we developed the Bluff system. We apply the same idea as in Summit, graph-based summarization, but here we focus on understanding when the model is not working well, what is happening. So we're showing you a screenshot of Bluff system where the network is under attack. Where the neural network is misclassifying giant panda images into armadillo images. So here in part B and part C here, you will see specific neurons that are manipulated by the attack. So particularly since we are changing or trying to fold the network into misclassifying giant panda and armadillo, so that means we might want to have some armadillo features like scales, bumps, and meshes like that to appear in the images through perturbing the images of the giant panda image. So this is what a lot of people have been thinking, oh, this is what is going to happen in images, but they do not know, or they did not know before Bluff, where this manipulation is really happening inside the model and which specific neurons that they are affecting. So here we can allow the user to pinpoint particular neurons that are vulnerable and the exact paths that the attacks are exploiting to lead to that misclassification. And after working on Bluff, then also got us thinking, well, maybe this idea of using visualization to understand attack can be extended to other models too, not only image classification. So that's exactly what we did for the SkeletonVis system that was published in AAAI 2021 as a demo, where we use visualization to help people understand how a human action recognition model may be under attack. So here we are showing an example where there's a video of a person doing lunges. So that means the benign classification should be lunges. However, the attack actually lead the human action recognition into doing a swing. So what we're seeing here is benign skeleton doing the lunges in green, and then the orange, which is here, you can see the skeleton actually got manipulated or distorted so much that it looks nothing like the human skeleton. Right? So some frames looks pretty good, but then for some frames, hugely distorted. So again, like through visualization or only through visualization, we can see that, so the attack is actually not really attacking all frames or the skeleton on all frames. Rather, it actually only need to manipulate a few frames of the video, and then that is enough to change the whole action recognition to swing from doing lunges. So far what I've shown you are a few example work in scalable interpretation, and also how it prompted us to develop the techniques further to help with understanding vulnerabilities and biases. Certainly, there's quite a few other work that I haven't talked about. Through doing all this work, something we encountered was that sometimes in order for us to develop these techniques, we actually need to learn about how these models work ourselves. For example, we say, I want to interpret a CNN, right? So we better know how CNN works. So this is exactly the motivation for us to develop the third line of research we call interactive education, which actually started again as an internship project for GAN Lab and back in 2017, which is the very first work where we say, so maybe it's really helpful to develop these education tools so that can help either expert or non-expert to understand how these tools work. So GAN Lab was originally an internship project, so again by Mr. Khan. And also with collaborators, mentor Nikhil, and also Fernanda and Martin, who are now a faculty member at Harvard. And GAN Lab, as the name suggests, as to help with understanding GAN, or generative adversarial network. And GAN, you probably have seen a lot of examples these days. Is often said as one of the most exciting, interesting idea of machine learning. And here I'm showing the example images. You've probably seen a lot of these, faces that look really real, but actually fake. And GAN is also the technique that behind deepfake and also many other related techniques. So a question here is that how do we help experts understand how GANs work? And again, motivation there is because GAN is actually really hard to understand even for experts. So, and the particular reason is because that GAN uses two competing neural networks internally. And to explain that, I can use the everyday analogies. Let's say there's a counterfeiter whose goal is to make fake bills, and then police whose goal is to spot fake bills. So internally at GAN, of course, we don't have counterfeiter or police. Rather, it actually has these two neural networks, generator and discriminator. So you can think of generator as a counterfeiter who's generating this synthetic data with the goal of trying to make these synthetic data look as real as possible. And then the other neural network inside, we call it police, or technically we call it discriminator, whose job is to spot the fake or synthetic data. Initially, when the counterfeiter is generating this data, they're not really good at it. So the original first version of the fake bills are very easy to catch. So police can easily catch it. And the reason is that police have access to real data. So it can do very easy comparison. And of course, the counterfeiter gets better. Like after getting caught, okay, second iteration get better. And the police also get better because then there's, so it's actually not as easy now. So it need to get better. And this keep repeating until at the very end that the counterfeiter is so good at making these fake data that the police can no longer differentiate the real one and the fake one. Then this is the time where the training can stop because the counterfeiter says, okay, this is great. So that I can just keep generating these fake data. So this is exactly the idea of GAN, where the generator network inside GAN is to generate this synthetic data starting originally in not so good way, but over iterations it becomes better and better. And then at the end, synthetic is so real that the discriminator can no longer differentiate. So the main question now, going back to visualization, is how do we help experts understand these dynamics, and also how to help them, let's say, to tweak the parameters of generators, discriminator, and so on. So we actually try quite a few ideas. First is that we just show the parameters as sliders and so on, and turn out to be really disastrous because the researchers really have a hard time giving a mental model of like what is really happening, which sliders correspond to which network. So what we end up doing through some iterations, we actually exactly take advantage of an analogy that we just look at. Whether we say, well, actually because that is pretty easy to understand, so why not we just build that into the visualization tool? So that's exactly what we did. So here's a screenshot of GAN Lab. So it's a live tool. You can go to the URL there and then try it live on your computer. No need to install anything because it all runs in your browser, no special hardware. So what we're showing here is that we have two big boxes on the left-hand side. So the purple one is the generator, and then the blue one is the discriminator. So you see that the generator is evolving over time. So initially, it wasn't looking that similar to the real data, which is a ring in green. Right? This is a data set that the user had drawn. And then you'll see that the purple dot, the fake data, over iteration, that look becomes more and more similar to the green dot. So through iterations, the user can see these in real time, and they can also change the parameter in real time and see how these parameter changes affect the quality of the improvement. So when we released GAN Lab, so it got a lot of interest. So it went viral on Twitter and social media, and then also it got a lot of GitHub Stars, and now it's visited by tens of thousands of visitors over the world. So after developing GAN Lab, actually that got us to step back a bit and say, wow, so GAN Lab was developed for many experts. But what about non-experts? Let's say for students, or maybe for newcomers to deep learning, or maybe for anyone who want to help people more easily understand these techniques. So can we apply the same method? Short answer is yes. So that led us to develop this CNN Explainer tool, which is using the model of the GAN Lab, where it's also a web-based tool. So you can go to the URL up there and then try it yourself. Again, no need to install anything. So the main idea of a CNN Explainer is that through the visualization, we allow the user to zoom in, to drill down to particular layers of a model. And then also through interactive visualization, we show them how the math is working. For example, CNN, it has a convolutional neural network, so there's convolution happening. So by clicking on specific layers, specific operation, so you can see, the convolution is actually done in this way, sliding a window through the particular images, and then that is how we reach the final prediction. And the ease of going between these abstraction level from the very high level overview down to these lowest level, the math, that we think is really, really helpful in connecting the high level concept and then the low level details. And CNN Explainer, as again, when we first released it, it also went viral on social media and got a lot of interest. And also now it's used in multiple courses and machine learning courses around the world. So far we have looked at a few examples in all the three categories of scalable interpretation, understanding vulnerabilities and biases, and interactive education. And I'd like to conclude the talk by giving a pointer to a survey that we did right after Activis and while we're working on GAN Lab. So that is the integrative survey for the Next Frontiers work. And it's led by Fred Holman, who's now at Apple, a research scientist there. And we use a 5W&H framework to summarize what all the visualization work that has been done at that point, up to that point. For example, like why they were developed, like what they developed for, when is it used, for example, while the model is being trained, after training, post-hoc analysis, who they are building, these tools are built for non-experts, like model users, non-expert, and so on. And what are the techniques, like how? So we do this summarization all for you. So I highly recommend that you check it out, particularly if you're new to visualization or deep learning or interested in learning more about it. And certainly we benefited from it ourselves because by doing the survey, then we know, so there are these open problems that we haven't solved, and that led us to a lot of the work that we do and what I shared today. And there's a newer survey that I also like to point out, which is on the left-hand side here, which is the comparative analysis of industry-human AI interaction guidelines. So this is a very interesting read because these are about all the big companies like Google, Microsoft, and Apple, about what they think the AI may be or should be used, and what are the interactive user interfaces that may be designed to support their use. Very interesting read because you'll notice that not all the times that the companies agree with each other. So looking at a comparison really give a lot of insights there. With that, I'd like to thank you all again for having me today, and also special thanks to my students. All the work that you saw today are done by them. And also I want to thank our sponsors and funding agencies for our work. Thank you very much.